Hello everyone, welcome to Arvind EduTech, and in this video we are going to understand the atomic model proposed by J.J. Thomson and Rutherford. So let's understand the atomic model of J.J. Thomson. So J.J. Thomson said that the atom is a sphere body which is made up of entirely by positively charged matter, and the electrons are uniformly distributed just like the seeds of the watermelon in the watermelon or the plum in the pudding. So therefore it is also called the plum pudding model. Plum pudding model. As you can see the picture, the it's a solid sphere. The atom is a solid sphere, and all the electrons are uniformly or randomly distributed inside the atom. So through this model, Thomson explained that the mutual repulsion of the electron is balanced by the attraction with the positively charged matter, and therefore the atom is stable and electrically neutral. He also explained the chemical reaction and radioactive disintegration through this model. But what were the reasons behind the failure of Thomson's model? So one of the reasons that this model could not explain the spectral series emitted by the hydrogen atom. So here you can see the series of the spectrum. It could not explain. Also, it could not explain the large angle scattering of alpha particle in Rutherford's experiment. Rutherford's experiment, which we are just going to learn. So, two of the students of Rutherford, Giger and Marsden, in 1911 performed the alpha particle scattering experiment to know the structure of the atom. To understand this experiment, first we have to understand what is alpha particle. So an alpha particle is a helium atom from which both the electrons have been removed. As you can see in the helium atom, there are 2 electrons and 2 protons in the nucleus. If you remove 2 electrons, it becomes alpha particle. So to perform this experiment, they took a source, radioactive source of alpha particle, and the beam was allowed to fall on the gold foil. The beam was allowed to fall on the gold foil. The gold foil was so thin. It was a thin gold foil. Its thickness was about 2.1 into 10 to the power minus 7 meter. The alpha particle scattered in all directions, and it was observed by a rotable detector which consists of a screen made up of zinc sulfide. The layer was there of zinc sulfide. Okay, and the microscope observed the scattering of the alpha particle. So whenever the alpha particle scattered through screen, it produces a tiny flash which was observed by the alpha particle. Now, what was the observations from this experiment? So the first observation was most of the particles pass straight the gold foil or suffers a small deflection or almost no deflection, or suffers a very small deflection when they pass through the gold foil. A few, it means 1 in 8,000 get deflected through 90 degree or more, and very rare, occasionally, I would say, the number is not possible, but very occasionally the alpha particle just retraces its path or just return to into 180 degree. So what was the significance of this observation? What were the significance of the result? First of all, through this experiment, the Rutherford concluded that most of the space within the atom must be empty, because most of the alpha particle suffers almost no deflection. So most of the space inside the atom must be empty. Also, the mass of the atom is concentrated in a very small region, that is called nucleus. mass of the atom is concentrated in a very small region that is called nucleus. So nucleus is very small with respect to atom. So you can imagine how small the nucleus is, that if your room is the atom, the tip of the needle will be the nucleus. So this is almost, you can say, the ratio of the atom and the nucleus. And the total negative charge is equal to the total positively charge of the nucleus, and therefore the atom is electrically neutral and stable. So you can see most of the alpha particle suffers no deflection, a very small deflection. So the alpha particles which comes in contact of nucleus get deflected through a large angle, and some of the alpha particles retraces its path and return back in 180 degree. As you can also see the graph where some theoretical data and the experimental data are there. So the circles are showing the experimental data, and the curve is showing the theoretical data. So you can compare it. And so atomic model of Rutherford says that the atom consists of a small massive center core in which the entire positive charge and almost whole mass of the atom are concentrated, and that is nucleus. So in the nucleus whole mass is concentrated. The size of nucleus is very small, as I told you, and the number of electrons is now equal to the number of protons, so it is electrically neutral. The electrons also revolve around the electrons also revolve around the nucleus, just like the planets revolve around the sun. Just like the planet revolve around the sun. So what were the so through this experiment they also tried to know the size of the nucleus. For that they took an approach, that is called the distance of closest approach, and the distance of closest approach estimates the nuclear size. So we know that the alpha particle is the positively charged particles, and when they try to enter the nucleus has the positive charge which repel it, and the kinetic energy is converted into the electrical energy. So when the alpha particle comes very near to the nucleus, it stops for a moment and then retraces its path, return back to with the angle of 180 degree. So from the distance where the alpha particle gets returned, that distance from the nucleus is represented by r naught, and this r naught is called the distance of closest approach. This r naught is called distance of closest approach. See, we know that the charge on alpha particle is plus 2e, and the charge on the material, here we have taken foil, but I am taking Ze, and the kinetic energy of the alpha particle is half mv square. So this energy of electrostatic energy is equal to k 2e into Ze upon r. According to the conservation of energy, the kinetic energy is equal to here the potential energy, and half mv square is equal to k 2Ze square upon r. So if we calculate, and this r will be represented by r naught, the distance of closest approach. So we'll get r naught is equal to 4kze square upon mv square, and this is the formula of distance of closest approach, where k is the electrostatic constant. You know, that's 9 into 10 to the power 9 newton meter square per coulomb square. Z is the atomic number, E is the charge on one electron, and m is the mass of proton. Because all the values we can put here, and for gold we can take Z is equal to 79, and through the calculation we'll get about 4.13 into 10 to the power minus 14 meter, or we can say 14.3 Fermi. We know that 1 Fermi is equal to 10 to the power minus 15 meter. Though the size is much greater than the sum of the size of the nucleus of helium and gold. Now we have to understand impact parameter of in this experiment. The impact parameter is simply the distance of alpha path of the alpha particle from the center of the nucleus, perpendicular distance of velocity vector of the alpha particle, and the center of nucleus when it is far away from the atom. So you know, the distance from nucleus center impacts the deflection of the alpha particle. So if the distance is more from the alpha from the center of the nucleus, the deflection will be less. There will be smaller deflection angle of deflection, and when it is passing through very near from the nucleus center, there will be a large angle of deflection. So this impact the deflection of this distance impact has an impact on the angle of deflection of alpha particle, therefore it is called the impact parameter. So the shape of the trajectory of scattered alpha particle depends on the impact parameter and the nature of potential field. The value of impact parameter can be determined by this formula: 1 upon 4 pi epsilon naught ze square cot theta by 2 1 by 2 mv square. You know all the values. E, Z is the atomic number, E is the charge on one electron, theta is the angle of deflection, m is the mass of proton, and v is the velocity. So we are now going to understand what were the limitations of Rutherford's atomic model. First of all, the Rutherford's atomic model suggested that electrons are accelerating around the nucleus, moving in accelerated motion. But we know that accelerated charged particle is the source of electromagnetic waves. So it must be radiating some electromagnetic radiations, and when it is moving and radiating electromagnetic radiations, slowly its energy will decrease, and it must follow a spiral path. Let me show you. Then it must follow a spiral path, like the electron should revolve like this, and finally it should collide with the nucleus, and the atom will be finished. So but that is not happening experimentally. We know that the orbits are stable and the atom is also stable. So secondly, in Rutherford's model, an electron can revolve in any orbit. So it should emit the continuous spectrum. But atoms like hydrogen always emit discrete line spectrum. So the Rutherford's atomic model could not explain this. So in the next video, we are going to understand the Bohr's atomic model. Thank you so much. Please like and subscribe the channel. See you.